Hello seniors, continuing with this class, electronic assignment number 3, tangent and derivative of x to the power of n. We're going to continue with the exercises where we left on yesterday. So remember, yesterday we have seen different concepts like secant line, tangent line, normal line. All of this in order to understand what the definition of a derivative is, right? So we've seen that the concept or the definition of derivative is the f prime of x, that's the derivative of function f, equals the limit when h approaches 0 of this, f of x plus h minus f of x divided by h. We make the demonstration about where that comes from. We did this explanation over here in order to determine that definition, which we informally defined as this. The derivative of a function is a gradient or slope function of the tangent line to a curve at a given point. That's the definition of a derivative, of the derivative of a function. So applying this concept about the limit, we solved this first exercise by applying exactly the same concept I just told you. And we were able to determine the derivative function, which in this case was 2x, and then we found the slope or gradient of the curve when x equals 3. And that was basically just to replace the value of x into the derivative function by 3. So we found that the slope, the slope of the function at x equals 3 is equal to 6, okay? So we're going to do some more exercises using the same definition of a derivative in order to make this a little bit more clear. And then we're going to see a shortcut in order to do this much easily. Okay, so it says use the definition of derivative to find the derivative of f and hence find the gradient of the tangent line at a given value of x. So we want to find the derivative function of this function over here and then evaluate that gradient function for x equals 2, and I added here for x equals 8. So for number 1, we're going to apply the same concept. We know that the f prime of x, the derivative of f, is equal to the limit when h approaches 0 of f of x plus h minus f of x divided by h, right? So let's identify the different terms we have here. F of x plus h, in this particular case, remember this is a function, so f of x plus h would be 2 times x plus h minus 3, right? This would be our f of x plus h, and our f of x is directly 2x minus 3. 2x minus 3. And then h is just h, so we're going to leave it like that. So if we replace those values here, we're going to say that this is equal to 2 times x plus h minus 3 minus parentheses 2x minus 3 divided by h. Okay, so we first try replacing the value of h with this value 0 and see what happens. So if we do that, we're going to get the following. 2 times x, right? So that's 2x. Let me write step by step just to make this clear. So 2 times x plus 0 minus 3 minus 2x plus 3 divided by 0, right? And if we perform this, if we keep on expanding this, this would be, I'm going to continue down here. This is 2x. The 3 cancels out with this 3 over here. So let me just use a different color for this. By. And then this is minus 2x divided by 0. Divided by 0. So this is the famous 0 over 0 case, which is an indetermination. Since this is an indetermination, we need to do something about it in order to solve the indetermination. So what I'm gonna do here is I'm gonna see if I can, before, let me see, we can expand this. So if I work with this equation, let me write it here. I'm gonna copy this. If I copy this down here, then we would say that this is equal to, if I expand this, this is 2x plus 2h minus 3 minus 2x plus 3 divided by h, right? So if I simplify like terms, this one goes with this one disappears with this, we're gonna get 2h over h. And you see that here the h simplifies, h and h, so we get a number here which is 2. And you see that in this particular case, the gradient function, so let me write this as f prime of x, the gradient function, is equal to 2, right? And it's completely independent of x. There's no x as we had in the previous example. Here we had 2x, right? In this case, the gradient function is independent of x. That means that no matter what the value of x is, the slope will always be 2, right? And if you pay attention to what type of function is this, if you noticed, this function is a linear function, right? And the linear function has one particularity, that is that its slope is constant throughout the whole line, right? It's always 2. It's not varying as it is varying in a parabola, for example, where for this point we have a gradient like this, for this point we have a gradient like this, and so on, right? So in the case of a parabola, the slope is varying, but in the case of a line, the slope does not vary, and that's why it's a constant number, which is 2, right? So if we want to find the gradient of the tangent line at x equals 2, we're going to say that this is f prime of 2, and this is still 2, right? Because it's independent of x. And if we want to find the value of the gradient of the tangent line for x equals 8, this would be f prime of 8, and it will still be 2, okay? There we go. There you go. So that's it for the first exercise. Let's go to the second one. Let me divide this just to avoid confusions. So for the second one, it says, well, we're going to do the same thing, but now for this function, which, if you see, is a quadratic function, right? So let me first identify f of x. In this case, f of x equals 3x squared plus 2x. And f of x plus h, in this case, would be equal to 3 times x plus h squared plus 2 times x plus h. Okay, so now if I apply the concept of derivative of a function, we would say that this is equal to f prime of x is equal to the limit when h approaches 0 of f of x plus h, which is all of this. So I'm going to write that here. 3 times x plus h squared plus 2 times x plus h divided by, minus, then I need to write f of x, which is, in this case, parentheses, 3x squared plus 2x, right? Let me correct that, plus 2x divided by h. Okay, so to find the limit, I'm going to first try to replace the value h into this function and see what happens, okay? So if I do that, we're going to get 3 times x plus 0 squared plus 2 times x plus 0 minus 3x squared minus 2x divided by h. Okay, and if you keep on simplifying this or expanding this, we would get 3x squared plus 2x minus 3x squared minus 2x divided by, sorry, this h, the h on below should already be 0, right? So divided by 0. Let me change this here. It should be already 0. So you see that if we simplify like terms, this goes out with this and this with this. So we're once again getting 0 over 0, which is an indetermination. So we need to solve for this indetermination. So what we can do here is, just as we did in the previous example, we can expand this and try to see what happens. Okay, so if I expand this expression over here, we're gonna have 3 times x squared plus 2xh plus h squared plus 2x plus 2h minus 3x squared minus 2x, right? This is all divided by h. And I can keep on expanding this by distributing these numbers over here, or these values over here. So we're gonna get, let me do that here. This would be 3x squared plus 2xh, sorry, plus 6xh plus 3h squared plus 2x plus 2h minus 3x squared minus 2x. This is kind of long, divided by h. So let's see if we can simplify like terms. Yes, we can. For example, this one cancels out with this one. 2x cancels out with negative 2x. So, and can we do something else? No. So let me rewrite this orderly. This would be 6xh plus 3h squared plus 2h divided by h. And if you notice, I have a common factor on the numerator, a common factor of h. So I can take that common factor and we would have h, and inside the parentheses I'm going to be left with, I think I'm missing something here. No, I think it's fine. Okay. So this would be 6x plus 3h plus 2, right, divided by h. And here I'm simplifying what is causing the indetermination, which is the value h. This cancels out with this. So now, once again, if we try substituting the value h with 0, which is always the value of our limit, of what the value of h we're approaching to, then this would be equal to 6x plus 3 times 0 plus 2. And this would give us 6x plus 2. And this would be the answer for the gradient function. So f prime of x is equal to 6x plus 2. After all that process, we got this result. This is the expression for the gradient function. So we want to evaluate this gradient function for x equals -3. So what we're going to do is basically find f prime of -3. And that means replacing the value of x with -3. So this is 6 times -3 plus 2. And this gives us This is equal to negative 16, right? This means that the function is decreasing, right? Because the value of the slope is negative. The function is decreasing for x equals negative 3, okay? Later on, we're going to be analyzing all of the graphical implications of derivatives, but I'm starting to make you think about these concepts already. Okay, so this is our gradient function, and this is the value of the slope for x equals negative 3. The value of the slope of the function for x equals negative 3. Okay, we're gonna do now the third and last exercise from this particular example. Number 3. It says we want to find the same thing, gradient function for this expression, which is also a quadratic function, and we want to evaluate it for this particular value of x equals 1. Okay, so we're going to do exactly the same process here. First of all, we're going to identify f of x, which is equal to x squared minus x plus 2, x squared minus x plus 2. Yes. Then we're going to identify f of x plus h, which is equal to x plus h squared minus x plus h plus 2, right? So if we apply the concept, f prime of x equals the limit when h approaches 0 of f of x plus h, which is all of this, so x plus h squared minus x plus h plus 2 minus f of x, which is all of this, so x squared minus x plus 2 divided by h. Once again, we need to try the indetermination. If we replace the values of h with 0, I'm going to try to do this a little bit quicker. This would be equal to x squared minus x plus 2 minus x squared plus x minus 2 divided by 0, right? So we see that on top, on the numerator, once again, all of the terms are getting simplified. So this is equal to 0 over 0, which is an indetermination which we need to solve. So to solve this, once again, we're going to expand all of this and see what we can do, what factoring case we can later do. So x plus h squared, that is x squared plus 2x h plus h squared. Then it's minus x minus h plus 2 minus x squared plus x minus 2 divided by h. So let's simplify like terms, if any. Let's see, x squared cancels out with x squared, x cancels out with x, positive 2 with negative 2, and I think that's it. So if we rewrite this, this would be equal to 2xh plus h squared minus h divided by h. So once again, if you see here, we can do a common factor, right? Common factor of h. So common factor of h, and this would be equal to h times 2x plus h minus 1 divided by h. Here we simplify the term that is causing the indetermination. And once again, we're gonna, let me write this here as 2x plus h minus 1. So now I'm gonna replace the value of h by 0. And we're gonna get 2x plus 0 minus 1. So this would be equal to 2x minus 1. So the value, or the gradient function, f prime of x, in this case is equal to 2x minus 1. And if we evaluate this, let me frame this. If we evaluate this for, I don't know what happened. if I evaluate this for x equals 1, then we will have f prime of 1 equals 2 times 1 minus 1, and this is equal to 1. Okay, that means that the slope of the function when x equals 1 is 1. Okay, that means that the function is increasing for this particular value of x. Okay, so I don't know if you noticed some kind of pattern here. When we did the first exercise, this was a linear function, right? And we got, as a result for the gradient function, a constant term, which is 2, which is not coincidentally, it's actually the same value as the slope of this line, right? So the gradient function, in the case of a line, matches the gradient of the line, right? But because that's the concept of the gradient function. It's the gradient function of a given curve at a given value of x, right? That's the concept of derivative. Now, if you look at the second example, this is 3x squared plus 2x, and as a result for the gradient function we got, let me see here. So if we compare this function to its gradient function, it's 6x plus 2. You're gonna, if you don't see the pattern, you're gonna see it in a second. But basically what we're doing is we're taking down this exponent over here. It multiplies the 3. 2 times 3 is 6. And the exponent is reduced by 1. Okay, so 2 minus 1, that's 1. So that's why we get 6x down here. And in this case, 2x, if we follow the same process, this has exponent 1, so we take the exponent in front. 2 times 1 is 2, and the exponent of the x is decreased to 0 now. So that's why the x disappears, and we get this 2 down here. Okay, so that's the pattern. And if you do the same thing for number 3, the same pattern, you'll notice that you're gonna get 2x here minus 1 over here, which is exactly the gradient function we got here, 2x minus 1. Okay, so that is what is explained here. Let me see how we're left with some. Okay, I think I'm gonna finish with this example, and then we're gonna leave the rest for another class. Okay, here is where the power rule comes from. So all of this definition about limits, about gradient function being the limit where h approaches 0 and all of that, is summarized into this rule. Okay, it is very important for you to know this concept that we've seen previously, but in a normal IB exercise, you would normally not use the concept to find the gradient function, but you're going to directly use this power rule, which is explained here. And let's see what this is about. It says, if f of x is x to the power of n, then the gradient function is always like this. It's the exponent, we take it down, that's why we have an n here, and the exponent is reduced by 1, okay? So that's how we find the gradient function quickly, okay? Once again, let me repeat this. We take the exponent down here in front, and the exponent is reduced by 1, okay? So let's try doing these 3 exercises over here before we finish, and you'll see that this is very simple. So for part A, we have f of x, let me write that here, f of x equals x to the power of 12, sorry. So if we follow the rule, we need to find f prime of x, we need to take the exponent down, so this would be 12x, and the exponent is reduced by 1. So if it was to the power of 12, now it should be to the power of 11, right? And that's it. This is the gradient function for this particular function, okay? This was an easy example. Now, look at B. We're going to get with some more complicated examples later on. We have f of x equals 1 over x cubed. Before we can actually find the gradient function of this, we first we should always have x in the numerator, okay, on top, right? We cannot apply this rule if the x is in the denominator. So in order to take it up, remember properties of exponents. This is the same as saying x to the power of -3, right? And once we write it like this, then we can find the gradient function, okay? So to find f prime of x, now that it is written in the proper way, f prime of x would be equal to, same rule. We take down this exponent, so it's -3 times x, and then this would be -3 minus 1, and it is -4, okay? Do not make the common mistake of writing -2 here, because -3 minus 1 is actually -4, not -2, okay? So this is the gradient function, and if you want to write it in a more fashion way, we could say that this is -3 divided by x to the power of 4. So this is the gradient function of this particular function we had here, okay? F of x equals 1 over x cubed. Finally, I don't know what's happening with my, and there you go. Let me do a short separation here to avoid confusion up to there. Actually, I think I'm gonna take this here, there. That's better. So let's divide this. Let's divide this. Okay, so part C. Now the function is f of x equals square root of x. How can we find the gradient function for square root of x? If you remember, once again, from properties of exponents, how can we rewrite square root of x using exponents? Remember, this is the same as saying x to the power of 1/2, right? It's the exponent in the radical, in the denominator, and the exponent inside in the numerator, okay? So once we have it written this way, then we can apply the power rule, and we would say that f prime of x is equal to, we take the exponent to the front, so this is 1/2 x, and then 1/2 minus 1, let me write all of the process here, 1/2 minus 1, that's actually -1/2, so this is equal to 1/2 x to the power of -1/2, right? And if we rewrite this into a fashion way, we could say this is equal to 1/2 of let me extend this, of x to the power of +1/2 over here, which could be written in a more fashion way by saying that this is equal to 1 over 2 square root of x, right? And this would be the gradient function in this particular case, okay? So I hope you're understanding this, people. It is a very, very mechanical rule. It's easy. You're gonna practice with some extra exercises, so don't worry. And you'll see that you will be able to find the derivative of any type of these functions, x to the power of n, very easily later on. Okay, so I hope this class was clear. If not, please let me know, and we can clear the doubts in a live session. See you, seniors.